this topic, this sort of presentation is specifically going to be about providing ancillary services. So there's some other aspects of it, like we can provide for improved efficiency by tracking the most efficient operating point of the turbine. I'm not really considering this at this point. So what I'm going to talk about is, so first I'll talk a little bit about ancillary services, what they are, what ones we're particularly interested in. I will show a little bit about, I'll introduce the simulation model that I have for the hydropower section, and I'll show that in the context of a conventional hydropower scheme and show maybe why it's a bit limited in the services it can provide. And that will then lead on to the variable speed system and all the many layers of controllers that we need on this thing. So I've created a basic control system that can provide some frequency support services, and that's what I'm going to be talking about. And yeah, this will hopefully lead on to something a bit more advanced. So with this system that I've got, I'll show a little bit of some of the basic functionality of it: the frequency response services, fast start, synthetic inertia, and then finally this will all be just, it's simulating a system connected up to a stiff grid, essentially, where I can vary the frequency and see what happens. And I'll then go on to showing what happens when it's connected onto a bit more representative grid. And this is using a model that was released earlier in the process. It was one of the earlier deliverables created by one of my colleagues. And then I'll give some conclusions. So ancillary services, it's basically optional services for which the generator can receive payment, like above and beyond just generating power or providing the functionality that they have to provide. So we've got frequency support, primary and secondary are kind of defined by the time in which they occur, and some grid operators, I believe, define a tertiary response, but the timescale is so long that it's not really of interest here. There's other services. Fast start, you can be paid to be able to start up from nothing to a certain power output within a certain time. Black start, not really considering that here. Voltage support, that's provision of reactive power to support the voltage, could be mandatory. And finally, possibly synthetic inertia. It's not really a thing that is an ancillary service at the moment, but it's something that may be introduced by some operators in the future. Particularly frequency response and synthetic inertia will become more important with the greater penetration of variable renewables. And these don't have any like grid connected or directly connected rotating mass. Wind might have a little bit of stored energy in the turbines, but it could be an issue to provide even synthetic inertia. It could get nasty couplings with the turbine mechanical dynamics. And solar, you basically get whatever the solar panel's putting out. There's no storage whatsoever. So as you increase the amount of variable renewables, you reduce the amount of generators that can provide the frequency response and inertia. So being able to improve these abilities is particularly important with a higher penetration of wind. So I'll be mainly considering frequency response first of all. So it's a response to a drop in frequency. So from the GB grid code, it talks about primary response as the power that's provided within 10% of the frequency drop, and sustained for a short period, 20 seconds or so. Secondary response is what's provided after 30 seconds, and it will be sustained for 30 minutes or so. So normally the plant response, as you can see, is kind of a mixture of the two of these things. And so this is a market system, or normally generators will bid for it in some form of market. They'll bid to provide primary response, that is only the amount of power that you are able to provide. So you bid to provide a certain amount of power. Secondary response, you bid to provide a certain amount of power, you get paid then for the energy as well. So this was the basic hydroelectric system that I've used. I've taken it from a paper that was provided by our colleagues at NTNU. So what you have is relatively high head system, 425 meters. You have a long head race. You'd have an underground surge tank and then a relatively short penstock of about 200 meters, and then a turbine. So this is a single turbine single turbine connected to single head race and penstock. It's an approximation of a more complicated system, I believe. So for the conventional system, you just got synchronous generator, governor driving the guide vane opening of the turbine based on the generator speed. And then you have a automatic voltage regulator controlling the generator terminal voltage. Relatively straightforward. So the model for this is based on, I believe, a relatively famous paper, but I've used a slightly different turbine model. This was based on, again, from NTNU. It's an Euler model that is kind of based on the mass flows and the water deflection by the blades in the turbine. So it can cover the sort of a simplified operation of the turbine over a fairly wide speed range, which a lot of the simplified models are based on a fixed speed and very small variations around it. So in terms of the waterway, I'm using a traveling wave model for the penstock, and then an inelastic model for the head race. This is also, it's discretized, so it runs at a slower rate than the power electronics models. I believe the power electronics models, the step size is about 50 microseconds. If you try and use that for the hydroelectric model or the hydro model as well, then you end up with a very slow simulation. So the hydro model is using a step size of 1 millisecond. So governor, relatively straightforward. You've got a generator inertia of 6.5 seconds. You have a permanent droop in the governor, which gives you about 20% increase in power for a 0.5 Hertz frequency drop. You have a regulator dynamics about 4 seconds, and then you have a limited gate opening rate. So what you have, the example here is a frequency dip at a time of 250 seconds or 50 Hertz down to 49.75 Hertz. So one thing to note here is that the power increase is very slow. So I think at 250 to 320, about 70 seconds, you're getting close to the final power. And you're limited by the sort of the need to not excite any undesirable modes in the waterway. Basically, you can't just turn this thing on and off really quickly. I should note that I haven't added in any transient droop control that could increase the performance. But the thing to note is after 10 seconds, that would be the primary response, you're only getting 1.3% extra power. After 30 seconds, you're getting 6.9%. Finally, you're getting about 9.4%. And an interesting thing to note as well is when you've got this change in grid frequency, you're getting a little extra electrical power here. That's from the inertia response. So variable frequency principles of that are, well, what you end up with is a complex arrangement with a lot of different controllers. They got turbine governor. This is slightly different in that rather than a fixed speed with a permanent droop, what you're using is a PI controller to regulate the speed using the guide vane opening. Your converters, you've got your synchronous generator. You've got a current control based on the for the field current. Machine side converter have a conventional DQ current control. And these are set by a flux vector control, so you can directly set the torque demand for the generator. On the grid side, again, you've got DQ current control driven by running through it with a PLL. DC link voltage control, I've got it kind of in the middle of everything. When you're running the thing normally, the machine side converter controls the power, the grid side converter regulates the DC link voltage. This is because the machine side converter is the slower of the two. You have a much higher inductance in the machine. So this just kind of ensures that you're not drawing power from the grid side converter faster than the machine side converter can provide it. However, when you're starting up and the machine's at a standstill, then you need to operate it in a different way. You need to use the grid side converter to control the DC link voltage. So there's a little bit of switching logic in the VDC control as well. And finally, grid control, this is providing your frequency response services on top of a permanent or a static power demand. So this, using a relatively fast sampling frequency for this control system, this is, it modeled as a 2-level average value model, but what I'm assuming is that the actual system would have a modular multi-level converter at this sort of power level. So modular multi-level converter will typically have a relatively high sampling frequency, but I've not considered an actual modular multi-level converter to avoid having to mess around with the internal control of such a device. So governor design was relatively straightforward. It's just a PID controller. This was again taken from the paper from NTNU. And you have some rate limits, opening limits, thermodynamics, and then an anti-wind-up system through back propagation, which stops the integrator winding up when due to the rate limit. So yeah, as an example of what it can do, this is the same frequency dip and droop settings as before, and this was then running the system with from an initial power demand of 0.5 per unit. And what you can see is electrical power goes up instantly as the frequency changes, and the generally response from the hydraulic system is fairly similar, but what you are in effect doing is you're allowing for a very fast response by borrowing power or borrowing energy out of the generator inertia. So you can see the drop in generator speed, and then it recovers as the hydroelectric system starts providing more power. So, this seems well and good. Job done. You can get lots of power, and you can get it instantly. The trouble with this is that there's a limit on what you can actually provide. If you're running the turbine at a relatively high power output and it doesn't have that much more that it can provide, and then you suddenly start asking for even more power, even if it could in the long term provide that power output. By suddenly asking for a large amount of power, you drop the generator speed down. When the generator speed goes down, you're then limiting the total power, limiting the power output of the hydraulic system or hydroelectric system. Then when you're still drawing more electrical power, the generator speed just drops and drops and drops and drops. This is an example of it. So you ask for lots of electrical power, generator speed just starts dropping, mechanical power can't support it, even with the guide vanes opened up to the maximum, flow goes up to a maximum, but yeah, you're just providing less power because you're limited in the torque when the turbine's slower. So eventually then the turbine will stop if you didn't have anything to deal with that. So yeah, sorry, I just got your question there. I'll answer the questions at the end, basically. So solution, you have just implement a bit of a smarter system. So one of the things you can do, you can provide a power limit based on the turbine speed. You can say, oh, what's the maximum amount of power that we can actually provide? And don't go above that. So, but yeah, the other thing you can do is split the response into a primary response and a secondary response. Primary response, it's fast. You've got a very short time constant on the filter here, but you've got then this system here that limits it to a slow, sort of a limited time period. Secondary response, a bit slower, but permanent. The key thing with this is I've implemented the power limit, but the power limit only limits the secondary response. So you can get some nice big boost of power off the turbine inertia. And then when you've got that, when that after like 20 seconds or so, that drops down to whatever the turbine can provide. So this is, for example, it's not great because we've got this huge, great legend stuck in the middle of the power graph. But what you can see is the green line here is the power limit. And as you suddenly ask for more, you suddenly get a grid frequency drop, you get a load of power from your primary response. This causes the generator to slow down. As the generator slows down, the power limit slows down. At this point here, then the primary response ramps down, you're getting back into secondary response. And then the generator is allowed to recover. So you're getting quite a lot of power at 10 seconds, a bit less secondary response, a bit more at the end. So I'd add that the speed limit or the power limit also allows a little bit of power to speed up the generator when it's if it's below the demand speed. So yeah, looking a little bit closer at that, you've got the power limit in green here, base demand of 0.75. Down here, you got in red the primary response, just sort of ramps up, ramps down again, and then secondary response slower. And you can see that it's the purple one is the demand, and it's following the primary response, and then it's limited during the secondary. So this turns out that this system of power limiting is actually quite good for fast start as well. So one of the limits with conventional hydropower for fast starting is that you're having to spin the generator up to the rated speed, which is quite slow due to the waterway dynamics and the generator inertia. When you got it up to rated speed, you then synchronizing with the grid, and then you're then opening up the guide vanes up to providing power. And this is, yeah, as I said, limited by the waterway dynamics and the governor bandwidth, and limited by the generator inertia. This could take up to 10 minutes for some systems. With variable frequency system, you're still limited by the generator inertia and the conduit dynamics, but you don't need the synchronization step. The converter can synchronize very quickly. it will just be waiting for power to be provided. And the important thing is you can start generating before the generator is up to the rated speed. So if you're only ramping up to 50% power output, then you don't need the generator to be running at the full speed. So if you only ramp the generator up to 50% speed, then that's a quarter of the stored energy. So it will be a lot quicker. So this is an example of fast start. So speed demand, you are asking for full speed, but only 50% power. The system's set so that the power is drawn once the speed exceeds, the generator speed exceeds 20%. So you can see you're starting opening the guide vanes, which ramps up the fluid flow, and you're getting your mechanical power up, and then the generator will start ramping up, and your turbine power starts increasing. It's limited by the power limiter. So power limiter limits the power until it can sustain that power level at about sort of 37 seconds. But in the meantime, it's limiting the power, but providing a little bit of margin to allow the generator speed to keep increasing. So finally, I'll sort of touch on synthetic inertia. This could be something kind of useful because, well, you're taking a grid system that's potentially low inertia, you're taking a hydroelectric turbine with quite a high inertia and then just putting it behind a converter. So you're further reducing the grid inertia, which is not really desirable. So one way of getting around this is to introduce synthetic inertia to the converter control. So this system that I'm using is based on a virtual synchronous machine. It's basically just using a proportional integral controller to set a virtual speed, integrating that to get an electrical angle. So a proportional integral controller isn't exactly the same behavior as a synchronous machine, but the integral controller is generally determines the virtual inertia, and the proportional controller provides damping. And I know that in the synchronous machine, the damping level is usually fairly low, but with a converter, you might want much higher damping. And one of the important things, a DQ current controller is still used in parallel. It doesn't do anything in normal circumstances, but it can provide current limiting during a fault. And this virtual synchronous machine is not particularly good with grid faults. So if you have a relatively large or a significant voltage dip, then you have to switch to the DQ controller. But you can switch, in my model, you can switch between them fairly seamlessly. So synthetic inertia, this is just response to a frequency dip. You've got an increase in the power demand in purple from the frequency support controller. But you also, in yellow, what the actual power is slightly higher. This is the inertia response of the virtual synchronous machine. So I think finally we get on to this grid connected mode. So this was this is a model created by my colleague David Campos earlier in the project, and I modified it slightly. So I think he'd had another thermal plant down here. I put in just basically another converter. I think to be more realistic, it probably needs a bit more hydropower and a bit more wind to like get a sort of a more extreme grid. And then our variable speed hydro plant is sitting down here. So I'll admit this model is, as it stands, is not a perfect scenario, and I was just basically trying to play around with it this morning to get something that looked an interesting looking scenario. It's not ideal, but it does provide some interesting results. So the scenario we got, I guess most of these wind converters at a fairly high output, the hydro plant, variable frequency hydro plant sitting about sort of 65%. Fixed speed hydro plant is about 75%. This thing's running at full power, and this thing's, I guess, a little bit of about 56%. So within this system, then you get a fault at 10 seconds that cuts off this plant here, and then we will see the response of everything. So yeah, one of the big issues is with at this point is with voltage regulation. So it's not actually, it doesn't seem to have the full voltage that it should do. So some of the loads are not as, the loads are basically resistive, so they're not providing full amount. And you get quite a big voltage dip because I guess a lot of these plants are not providing the voltage support like they should do. I haven't set them up right. So interesting consequences, you get this voltage dip, and that limits the power output that the wind farm can provide. Wind farm gets very confused with that. So again, something to look into. But as you can see, as you'd expect, you get a drop in frequency that causes the reactive plants to or the frequency support plant to provide more power. So one thing to note is that the fixed speed hydro plant is very slow in operating, but you can get the variable frequency one is then providing quite a lot of power as it should be. Actually, also, I don't know what these little glitches are in the virtual synchronous machine as well. So, looking at the turbine itself, you get this drop in frequency as you'd expect, and yeah, it's sort of behaving as you'd expect it to. You're not actually operating anywhere near the power limit, so the system's not, the controller's not doing anything particularly funky there. So in conclusion, I've got a controller to provide frequency response using variable frequency hydropower. It can also help assist with fast starting and synthetic inertia, but not done much testing with the grid controller or the full grid, and that needs to be done. Needs to sort out the voltage support and implement some more realistic grid scenarios, I think we probably need more hydropower and more wind power on this thing. So for the controller as it stands, one thing that would be I want to do is include more about the undesirable operating modes of the turbine. So I've got a power limit, and with a similar thing, you could say, oh, these particular modes of the turbine are undesirable. We will try and steer clear of that. But really, this is kind of a baseline controller that's to be compared to something that's a bit more intelligent that we're going to develop after this. So I know there's a lot of talk about model predictive controllers. That seems like a good option that could both speed up the response of the hydroelectric system, but also have a tighter coupling with the frequency support system. So finally, just a thought. So I've implemented synthetic inertia. I put in the inertia of the generator into the synthetic inertia, but you're not limited by that. So one option you could have is reduce the generator inertia. Possibly some generator designs could reduce the inertia, which could allow a much faster startup from standstill. But then this could have a lower transient power output during frequency support events. But maybe you could mitigate that with a better overall controller. Or another option might be to just even further increase the synthetic inertia to compensate for the lower inertia from having more solar or wind penetration. So yeah, those are just final thoughts, and thank you for listening. And do you have any questions?
Thank you very much, Max. Yes, as you said, if there are any questions directly related to the presentation that Max held, please come forward. You had one on the chat there. I don't know if you were able to read it. Asks
so
if
does the model of the turbine consider the fact that the turbine runner throttles the flow as the speed increases and vice versa, independently of the guide vane position? Yes, I think it does. So I actually, hydroelectricity is not my background at all. My background is more wind. So
I can see you mentioned Torbjørn Nilsen's paper reference. So I know at least that model does include this effect. So if you use that model and implemented it correctly, then you probably have included it.
Yeah, it's whether I implemented it correctly as well. That's the
Bo is here.
Yes.
Yeah, I have a question also here. You said something about that you can generate that, start generating already during startup of a generator, and not that generating power, not at nominal operational speed.
Yes.
Is there any investigations then? Because when I see it, this is a further, how to say, freedom in space then for the generator, which normally is not considered. The generator and also the turbine generating at not nominal speed with power. So is there any investigations what will that inflict on the generator and what will this inflict or mean for the turbine also? Because I would say, I guess the hill shots will become very complicated.
Yeah, that's the interesting thing, because I unfortunately don't know enough about the the turbines themselves, and I'd be interested to know about it. And I mean, my understanding is that they are designed to run at a single speed and sort of optimized around that. So if you start changing the speed that you're generating power at, then yeah, they might not be very happy about that. But
exactly. Yes, but if you have some collaboration, that was my second question. Sorry, you have some collaboration with the Hydroflex in is it called South Europe, or I don't know, because there are colleagues working down south also in this, and a lot with the turbines also, I think.
Yes, that is something that would be a useful collaboration that I've not sorted out yet.
Okay. Yeah, thanks.
May I just have a comment on this? It's Arne Nysson from NTNU. I think Igor, I think you are on the line as well. We had in the Hydrocell center, we just have Igor either here defended his thesis on a variable speed turbine. So maybe you could say a little bit about non-synchronous operation of the turbine then, Igor.
Hi, Arne.
Yeah.
Can you hear me?
Yes.
Yes, it's Igor here from NTNU. I defended my PhD thesis on design of variable speed Francis turbines. Could you, Arne, please repeat the question once again?
The question from Bo was then what happened then if you start producing, let's say, when you're reaching this 50 or 60% speed, then, such that you can start to produce earlier on, then you do not need to be at synchronous speed before you start. And then you have been doing some studies, and there's also design modification to adopt the Francis turbine to be operated at lower speed.
Yes, we did a research focusing on stretching the hill chart when utilizing variable speed. So yes, on one hand, it's actually possible to stretch the hill chart, but by designs, some turbines will allow you to do that, and other turbine designs will actually prevent you from stretching the hill chart by design, by hydraulic design.
Mm-hmm.
So of course, the more stretching we have in the hill chart, the higher efficiency and less pressure pulsations will the turbine have when operated at off-design operating conditions.
Mm-hmm.
So it is highly, I would say, case dependent. We cannot draw a general conclusion here. It doesn't works that easy for all sorts of Francis turbines.
Oh, I understand. Thank you for the comment.
Yeah, you're welcome.
Thank you. I suggest